Session is going to start in about 10 seconds. 9, 8. Trying to give people some time to actually settle down. Marcelo is running a very tight ship. Do we have the next speaker, the one right after this? Do you have your slides copy? Oh, thank you. All right, so welcome to POT session number 1 on graphs, hypergraphs, techniques on databases. The first talk is by Reinhard on a really difficult problem that has been open for a long time. I spent some time on this problem. I couldn't solve it. I'm very excited to hear about this result. Reinhard.
Okay. Thank you very much for the kind introduction. So let's start. When we look at 3 fundamental problems of computer science, that is conjunctive query evaluation, constraint satisfaction, the homomorphism problem, then we notice that essentially they're all the same problem. That is evaluating first-order formulas built from existential quantification and conjunction. And we also notice that the underlying data structure of these problems are hypergraphs. So let's look at a simple conjunctive query which asks for teachers who have a child enrolled in a course taught by them. In the hypergraph corresponding to a conjunctive query, the vertices of the hypergraph correspond to the variables of the query, and the edges of the hypergraph correspond to the atoms of the query. So here we have a query with 5 attributes and 3 atoms. Correspondingly, we have a hypergraph with 5 vertices and 3 edges. Classical results tell us that conjunctive query evaluation is a NP-complete problem in the general case, and it becomes tractable for acyclic conjunctive queries. So a natural question is, how can we get larger classes of tractable conjunctive query evaluation? And the key to this question, or to answering this question, are various notions of widths. So let's start with 3 widths and 3 decompositions. Let's look at a slightly more complex conjunctive query whose hypergraph looks like this. Now, a 3 decomposition of the query, or equivalently of the hypergraph, is a tree whose nodes are labeled by sets of variables, or sets of vertices of the hypergraph. And we call these sets of vertices, the sets of variables, bags. And these bags have to satisfy 2 conditions. The first one is that every atom of the query has to be fully contained, or the variables of every atom in the query has to be fully contained in one of the bags. So for example, if we look at the first atom, sorry, it does not really, this animation is not really visible. I highlighted the first atom and also the corresponding hypergraph, which unfortunately you do not see here now. And what can we do? Okay, anyway, so the variables of the first atom, okay, sure. On the screen you do not see the laser pointer either. Okay, fair enough. But actually you would see that the variables of the first atom are in fact covered by the root node of the 3 decomposition, or of the second node, of the child of the root node. If we look at the second atom, we notice it's also covered by the child of the root node of the 3 decomposition, and so on. And the second condition that 3 decompositions have to satisfy is the so-called connectedness condition. It means that the bags which share a variable have to occur in a connected subtree of the 3 decomposition. For example, here we have the nodes with the x variable, here we have the nodes with the f variable. We see that the nodes are connected. And the width of a 3 decomposition is the maximum size of the bags minus 1. So in this case, the maximum bag has size 9, the width is 8, and the 3 decomposition of a hypergraph is the minimum width that we can obtain over all 3 decompositions. in order to define further notions of width, we need to introduce edge covers. So suppose we are given a subset of the vertices, then an edge cover is a subset of the edges, such that each vertex of this vertex set V prime contains in at least one of the edges of the edge cover. And if we add these edge covers to 3 decompositions, then we get so-called generalized hypertree decompositions. So remember our conjunctive query and 3 decomposition we've seen before. Then if we look at the back of the tree node, of the root node of the 3 decomposition, we notice that a single atom, or equivalently a single edge, namely the J atom, suffices to cover all of these variables. If we look at the child node of the root node, we notice that we need 2 atoms, the A and the B atom, to cover all of the vertices, and so on. So we notice that edge covers of size at most 2 are needed to cover all of the backs, and so we say that this generalized hypertree decomposition has width 2. Again, the generalized hypertree width of a hypergraph is the minimum attainable. Hypertree decompositions are yet another notion of decompositions, and they are a special case of generalized hypertree decomposition where the so-called special condition is imposed. And it means that if at some node a variable disappears, like for example here in the node we see in red the J, X, and Y variable, which actually disappear here in the sense they are contained in the edge, but they are not contained in the back that is covered, then this variable is not allowed to ever occur again below, which actually is the case here. So this is a valid hypertree decomposition, and the width, of course, is still 2. So far, we have introduced edge covers as subsets of the edges. Equivalently, we could have introduced edge covers as weight functions, which either put weight 0 or 1 on each of the edges. And the vertices covered by such a weight function, denoted by B of lambda, are exactly those vertices which are contained in one of the edges of weight 1. And this notion now can be nicely generalized to fractional edge covers, where we allow arbitrary weight functions which put arbitrary values in the interval 0 and 1 on each of the edges. And now the vertices covered by such a fractional cover, denoted by B of gamma, are those vertices which are contained in a set of edges of total weight at least 1. And if we replace or extend integral edge covers to fractional edge covers, we get a generalization from generalized hypertree decompositions to fractional hypertree decompositions. So in this example, we have denoted the weight on each edge by the superscript. So for example, in the root node, the atom gets weight 1. In the node below, the 2 atoms both get weight 1. So far, this is still an integral cover, actually. But if we look at the node in red, we notice that it suffices to put weight 0.5 on each of the 3 edges, and we still manage to put total weight 1 on each of the vertices. So in other words, this bag has a fractional edge cover of size 1.5, even though every integral cover would require at least weight 2. But anyway, for the overall width of the fractional hypertree decomposition, we have to take the maximum weight over all of the edge covers, and again we end up with width 2 in this simple example. This one works. That's great. Okay. Thanks a lot. So by simply looking at the definition of these various notions of width, this sequence of less than or equal relationships for these notions of width for every hypergraph H are immediate. And what's the use of these notions of width? Well, it has been shown that if for a class of conjunctive queries, any of these notions of width is bounded by a constant, then conjunctive query evaluation becomes tractable. Now this immediately gives rise to another interesting computational problem, namely the check problem for the various notions of width. Here, for a constant value of k, we are given a hypergraph H, and we have to decide if this particular hypergraph has tree widths or, sorry, I can't operate it. Tree widths or hypertree widths, generalized hypergrids, fractional hypertree widths less than or equal k. And in case of a positive answer, of course, we also want to compute a concrete decomposition. Now, as far as the complexity of the check problem is concerned, the state of affairs is as follows. For tree widths and hypertree widths, it's known that the check problem is tractable. For generalized hypertree widths, it has been shown that this problem is NP complete for any value of k greater than or equal 3. Actually, the case k equals 2 is open. It looks like a small special case, but recent studies of several benchmarks and query logs of conjunctive queries have shown that this case of generalized hypertree width 2 is actually a quite frequently occurring case, so it's not an unimportant special case. And finally, for fractional hypertree widths, the complexity has been mentioned as an open problem in the Soda 2006 paper by Groh and Marx, and it has been open since. So the first main result of our work is to close these gaps. So we prove that the check problem for fractional hypertree width is NP complete for k equals 2. And as a side result of this proof, we actually also close the special case of k equals 2 for the generalized hypertree widths. So this NP hardness proof is very technical, so don't be afraid. I'm not going to show you details of this proof, but I would like to highlight some key ideas. So above all, it's a proof by reduction from the 3 subproblems. So we are given a propositional formula phi, and from this we construct a hypergraph H in such a way that the formula phi is satisfiable if and only if these two notions of width are less than or equal to. The easy part of the proof is the first implication. So suppose that the formula phi is satisfiable. We have to show that these two notions of width are less than or equal to, and actually it suffices to do so for the generalized hypertree widths because the fractional one cannot be bigger. Yeah? And to prove this implication, we take a satisfying truth assignment of the formula phi, and from this we construct the generalized hypertree widths of width 2. And this generalized hypertree width has a very specific form, namely it's a long path. The more difficult part of the proof is the opposite implication. That is, if one of the two notions of width is less than or equal to 2, then we have to show the formula is satisfiable. Again, it suffices to show this for one of the notions of width, namely for the fractional hypertree width. And we prove this implication by using specific gadgets which enforce a very specific form of any fractional hypertree widths of width, fractional hypertree decomposition of width 2, namely essentially a long path. And along this long path, we can then read off a satisfying truth assignment. I will briefly mention some of these gadgets. Suppose that a hypergraph contains a clique of size 4. In this case, we can be sure that there must be a node in the decomposition which has all of the endpoints of this clique in its bag. And of course, if there are several such cliques, then there must be several such nodes which contain all of these endpoints of each of the cliques in their bags. And now what we did is we added a set M1 of fresh vertices to each of the edges, A1, B1, B1, C1, and C1, D1. And we did the same with yet another set of fresh vertices or variables from the query, if you wish. We call this other set M2, and we added it to the edge A2, B2, B2, C2, C2, D2. And then it can be shown if the hypergraph contains such a gadget, then the corresponding fractional hypertree decomposition of width 2 must contain a node which has not only the endpoints of such a click in the back, but also all of the vertices occurring in M1 and M2. This can be shown, yeah? By exploiting the connectedness condition, which must hold for any decomposition. Now suppose that our propositional formula has n variables, x1 through xn. Then we actually added two such gadgets to our hypergraph, h0 and h0 prime. In h0, we have precisely the gadget on the left upper part of the slide, where the sets M1 union M2 on the one hand contain a large set of vertices S and a set Y consisting of vertices Y1 through Yn. And the other gadget, H0 prime, contains primed versions of this gadget on the top left, where M1 union M1 prime union M2 prime again contain exactly the same large set S, and on top of that, a set Y prime. And the intuitive meaning of this Y and Y prime variables is the following. We use the variable Yi to encode the truth value true of the propositional variable xi. And we use the vertex yi prime to encode the truth value false. Now the encoding of the clauses and enforcing that any fractional hypertree decomposition indeed contains a long path is very involved. I'm unable to show any details here. I just want to mention what each of the nodes along this long path essentially looks like. And each of these nodes consists of some set B1 of vertices, yeah, which just make the long path going without giving you any details. The set S is, as I mentioned before, some large set of vertices. And why is it large? Because we need several partitions, a big number of partitions into two subsets so that these partitions never interfere. And finally, each of these nodes contains a subset of the union of Y and Y prime variables. So in total, the intended decomposition has this picture. On the extreme ends of the long path, we have the nodes which cover the gadgets H0 and H0 prime. And look here, if there is a node which has all of this large set S together with the Y variables, and on the other hand, we have a node in its back has the large set S and the Y prime variables. And in between, we have this sequence of Zi, which contain a subset of Y union Y prime. And by the connectedness condition, it's clear that from left to right, the set of unprimed Y variables contained in the Zi's must be decreasing, and the set of primed Y variables must be increasing. And by enforcing n big enough, we get some point where the Zi and Zi plus 1 are equal. And at that point, we can read off the truth assignment. Actually, I took a bit too much time for the negative result. We also have positive results, namely, we identified tractable cases. And to this end, we identified relevant structural properties of the hypergraphs. One is the degree, that is the maximum number of edges in which a vertex appears. And the other one is the intersection size, that is the maximum number of vertices that two edges share. And we managed to show that in case of bounded degree and bounded intersection, the check problem for generalized hypertree widths becomes tractable. If we impose both restrictions, then also for fractional hypertree widths, we could show tractability. Actually, if I had had more time, I would give you some idea of why computing hypertree decompositions is easy because of the special conditions, And generalized Hypertree decompositions is hard because this special condition is missing. But if we have the bounded intersection property, then it becomes easy again. We actually generalized this result from bounded intersection to bounded multi-intersection. That is, it's not necessarily required that two edges have a small intersection, but a constant number of edges, say 3, 4, 5 edges share a small number of vertices. And also in this case, we managed to show tractability of the check problem for generalized Hypertree width. And actually, we also showed an approximation result for fractional Hypertree widths, namely, in case of bounded Vapnik-Chervonenkis dimension, we can, in polynomial time, approximate the fractional Hypertree widths up to a logarithmic factor. Well, VC dimension is itself an intractable property, but bounded multi-intersection implies the VC dimension. Now, the final question I want to mention in this talk is, are these restrictions realistic? And to this end, we analyzed several benchmarks of conjunctive queries and constraint satisfaction problems, and it turns out, well, the degree is not necessarily guaranteed to be that small, but the intersection of 2, 3, or 4 edges is always or almost always small, and the same applies to the VC dimension. So to sum up, we have closed this gap for the complexity of the check problem, both for the fractional and for generalized Hypertree widths. We have identified new tractable classes, and we have also proved an efficient approximation in case of bounded VC dimension. As far as future work is concerned, of course, we want to get similarly strong results for tractability of fractional as we have for generalized Hypertree widths. So actually, with bounded degree, we have meanwhile managed to show that that the check problem for fractional Hypertree widths is tractable by using deep combinatorial results of Soltan-Füredi. But for bounded intersection property, bounded multi-intersection property, this is still open. And of course, an important aspect is to implement these algorithms and to show if theoretical tractability and efficient algorithms in practice match. Thanks a lot.
We have time for maybe 2 questions.
Where do these constants figure in the complexity?
Sorry?
These constants, bounded degree, bounded intersection.
Sure,
Where do they appear in the complexity?
Yeah, sure, they're in the exponent. In case
the exponent of what? Do you get fixed parameter tractability there or not?
For bounded intersection, we actually get fixed parameter tractability. For bounded multi-intersection, this multi actually occurs in the exponent where the base has the size of the query. I mean, it's always, of course, exponentiality with respect to the query.
Yeah. But that makes a huge difference in the practicality of this algorithm, right?
Absolutely, absolutely. And so far, we have not yet implemented the theoretical tractability result for bounded multi-intersection. But for bounded intersection, we have quite promising results, actually. That works quite well. And even more so because, as we have seen on the previous slide, that in most cases, the bounded intersection size is really small. It's 2 in almost all of the cases. If you look at the conjunctive queries, there are a few exceptions with bounded intersection size 5. So this table is to be interpreted how many instances have a certain size of bounded intersection, of bounded multi-intersection. So almost all of the conjunctive queries we studied from various benchmarks have very low bounded intersection, and this really helped.
Thanks.
Thanks for this talk. I have a question about the hardness results. You said it's using decompositions like look like paths, like the decompositions that you have are path shaped.
Yes.
So does this mean this hardness already applies to like variance of path width for your context?
Sorry, but okay, but it makes a difference how you cover the backs along this path. If you allow arbitrary edge covers or arbitrary integral or fractional edge covers, yes, then the complexity, the full complexity is already there, even if you restrict the shape of your decomposition to paths.
Yeah.
But of course, if you're interested in path width, where you are interested in the size of the bags, then this is a subcase of tree decompositions. And tree decompositions, tree width is a tractable case for check problem.
But so this hardness result would already hold for some fractional path width definition or something?
Absolutely. Yes, absolutely.
Okay.
Yeah.
Interesting. Thanks.